draw linear algebra through geometry. So let's wait for a few more minutes and then we can start. Everyone, am I audible? Okay, great. So let's start the session. Right. Mm. Cheers. 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 Right. So is my screen visible? Is my screen visible?
Yes, sir. Yeah.
Great. Let's start the session. Yeah, so yesterday what we were seeing is we were solving problems from week 10, right?
Yes. You gave us week 10 problems and asked us
So
to
week
solve.
10 notes were over, right?
Right.
So let's solve these problems very quickly and then we can start the session for week 11, right?
Yes, sir.
So let A be 5 cross 7 matrix and B be this vector, which is basically 1, 2, 3, 4, 5, or 5 cross 1 vector, right? Suppose the best approximation of B in the column space of A is P, which is 2, 3, 2, 3, 5. Then the vector that best approximates B in the null space of E transpose is given by, right? So how should you proceed with the solution?
Uh, Sir, basically, we know how to approximate B on the column space of it, which we were doing all the times
Yeah,
for least square
right,
solution. So now we are asking the orthogonal case. Like we know that column space is orthogonal to the left null space.
right,
So now we are asking which vertical vector approximates this B vector, which is standing perpendicularly on this column space of it.
right, which is basically perpendicular to. So what will you do?
So yeah, so I was trying to go with B minus P, this kind of thing,
Yeah,
but
yeah,
it didn't result out to any of these given options. Then I tested which of the given options is perpendicular on the column space. Uh,
right,
so option C came to be true, but I was having the doubt. So initially I was thinking that B minus P would be the answer. The
okay,
direct answer would be B minus P.
right.
But B minus P is not coming. Is there any typo like in the B vector? Is there a miss pattern like 1, 2, 3, 4, 5? If it is 5, then the correct option would be C. Uh,
Okay, so let me just check once, right?
okay.
Yeah, so the B is 1, 2, 3, 4, 5, and projection is 2, 3, 2, 3, 5, right?
Oh, okay. Then it's fine. Here B is mistakenly written as 1, 2, 3, 4, 6. So I was having the doubt.
Oh, 1, 2, 3, 4, 5. Oh, sorry. Yeah, there should be 5 here. 1, 2, 3, 4, 5, right?
Okay, sir. Yeah.
There should be 5, right? So now your answer is B minus P, right?
Right. And it turns out to
So
be C.
minus 1, 1, minus 1, 0, right? Which is option? Wait a minute. B minus 3. 4 minus 3 is 1. Plus 1. Yeah, option C is correct, right? Any doubts? I think there are no doubts. B can be written as something in the plane of row space of column space of A plus something ortho to the in the null space of A. And the question is null space of A, something orthogonal to the column space of A. What is orthogonal to column space of A, which is null space of A transpose, right? Anyone do have any
Yes.
doubts? No, right? So let's proceed with this next problem. Consider the following system of linear equations. A equals to B. The matrix that projects 2.5, 5 onto the column space of A is.
Sir, here both option A and D seem to be true to me. Uh,
2, 2, 4, x1, x2, 2.5. Right. So now our question is we want to project 2.5, 5 onto the column space of A, right? So how will you proceed with the
Option C,
solution?
option C will be there.
uh,
Why?
no, it is already in the column space. It is already a 1 2. It is spanned by 1 2. No, already it is spanned by 1 2. So it is already in the column space. So D
Right.
could be answer that non-existent as the vector B already in the column space. But my doubt is
Yeah.
if I say just for the sake of argument, if I say that A is the correct answer, that A projects 2.5 2.55 to the column
Yeah.
space, then how am I wrong? Like identity matrix is indeed a projection matrix, and it is indeed projecting it to the very same space where it is already.
So what is wrong here?
So uh, I'm confusing between A and D. To me, both options are true for this particular question. Is it the case?
Acha, acha. No, but non-existent essentially means that such a matrix does not exist. Is it true? Like the matrix exists, right? So let's say if you have a projection matrix P, and let's say you have a vector V that is essentially in the space where projection is projecting it. So you will get PV equals to V, right? And this is perfectly defined operation, right? There is nothing stopping you from having such P, right? From defining such P.
Right, but how will you obtain that P? So by doing that A into A transpose A whole inverse into A transpose, right? Hello, sir, your voice is not coming. Satinder, can you hear?
Yes.
Oh,
Hello.
can you hear? Yeah, can you hear sir's voice, or am I the only one? I can hear you, Satinder, but I cannot hear sir's
Uh,
voice.
okay. Actually, which option will be correct now? I think option
No,
D
no.
will be there.
Satinder, can you hear sir's voice?
No, I think it is not audible just now. So
Yeah, right, right. Sir, no, sir, still not audible. Uh, I can see you're speaking, but
Okay, yeah, now I'm audible.
yeah, yeah.
Fine,
Now fine.
great, great. So what I'm saying is option D says that such a matrix cannot exist. What I'm saying is the matrix will exist, right?
Okay. But okay. But this is not the projection matrix for that projects onto the column space of A, right? For this particular 2.55, which is already in the
It's
column
not
space of A,
saying
it's what?
right, right, but it's not saying is this a projection matrix or not. It just says is there a matrix that projects this on space of A? The basic question. So identity matrix essentially does this, right?
uh,
Oh, okay.
excuse me, sir.
And I think there should be something in the problem statement like maybe that projects onto the column space of A orthogonally, some orthogonally, right? Because this B and C will also do some sort of projection, but
Mhm.
what kind of projection they will do that depends upon the application. If you talk about orthogonal projection, then option A is correct. Fine. Any doubts?
Okay. No, sir, no doubt.
Yeah, Satyendra, what was your doubt?
Just I was saying ki, it will be projected by 1 2 vector, no? Because if I'm going to take row echelon form, so by that it is coming 1 2, no, column.
One,
So
two.
it is in the 1 2 vector 1 2, like the first column. It will be spanned by the
Okay.
first column, no?
Right, right.
So B is already in the column space means.
Yeah.
So D
Right.
option cannot be.
D option, why should be there? Um, Hello.
Yes, sir.
So what I'm saying is, why are you assuming that D option will be correct? What is the reasoning behind that?
What I'm thinking ki like this B will be spanned by 1 2 vector, and it is already in the column space. So it is written, no.
So basically, you are
Okay,
saying
not.
C,
No, no. C will be not there. C will be not there. Okay.
right?
Non-existent. It is written, but it exists. I think it exists is in 1 2.
Yeah,
1
it
2 will be
exists.
the. Yes. So
Yeah,
1 2 we can write the basis as 1 0 and 0 1. A option is correct now. I've got it. Because
right.
1 2 can be expressed as 1 0 and 0 1 combination 1 2 will come. I think correct.
Right.
A option
Basically,
is correct.
the matrix is singular, right? That you can see, right? Can you see
Yes,
this?
the matrix is singular. So actually, I was having the trouble because I was thinking if I consider only the first column and I name that a matrix, uh,
Okay.
and if I try to find the projection matrix based on that,
Hmm.
so then definitely I'm getting a projection matrix which indeed projects any vector on the plane to the
Hmm.
column spaces of A.
Hmm.
But it was not turning out to be identity matrix. I can understand why identity matrix works for this particular line.
5 comma 5, right? So let's consider this problem statement, right? Now in the, let's say this is your space, 2D space, right? Now you have this space, column space of A, that is given as x1 comma 2x1, right? Which is essentially k times 1 comma 2. So it is essentially a vector that goes along this line. So all the vectors along this line will be in the column space of matrix A. Now the question is, which of the matrix projects the vector 2.5 comma 5, right? 2.5 in the x and 5 in the y, right? You want to project it on this line, right? So what you do, you see how it looks like, right? So this is basically, this will be your vector, and you want to project this vector on the line itself, right?
Right.
Now what now you don't need to think of anything else. Just remember how we used to do the projection step, right? So you have a vector that looks like, you want to project it along a vector 1 comma 2, right? So what is the projection matrix for a vector like that looks like this? U transpose by U transpose U. You remember this,
Right. Yeah.
right? So it will be 1 2 into 1 2 divided by norm, which is 5,
Right.
norm squared, right? Whatever.
Right.
And then you can compute this, 1 into 1, 1 into 2, 2 into 1, 2 into
Four.
2 divided by 5, right?
Yeah. So yeah.
So, so this will be your projection matrix along this line, right?
Right.
Now, uh, mm, so now let's try out if it is working actually. So this into
Let's say
uh,
7 3.
2.55. What does this give you?
Okay. Uh, wait
2.55.
first.
5 plus 10, 2.5 plus 5 for the 20 divided by 5. So this is 12.5 by 5, and this is 25 by 5, which is 5, right? And 12.5 by 5 will be 25 5s are 125, right? You get 2.5 comma 5, right?
Right.
So this will be your projection matrix that we are looking for.
So this projection
Now,
matrix indeed
yeah,
projects every vector onto that line. So I'm
onto that.
happy to say this a projection matrix for projecting any vector on the column space of A.
Yeah, this is the projection matrix that projects any vector on the column space of A. Now the question is, you have to choose one matrix among these matrices that projects this specific
Okay,
vector on the column space of A. Now for this, I can, like, this is a set, right? So this is a set. So let's define it as like this. This is a set S that contains this matrix, all this matrix, right? U transpose U. So let's call it projections, right? Projectors onto column space of A, and there is a smaller set in that, that is essentially identity matrix, that works on only for vectors in the column space of A, right? We can always say this, right? Can we?
oh yes, right.
Right? So this is a smaller set. And then the question is, so now you will have this set of points, all set of points, and this point 2.5 comma 5 will lie in this smaller set where the projector will be identity matrix. That's it. Fine.
Okay. So sir, also tell me, so in this Venn diagram, which contains
Hmm.
all projectors,
Yeah. From here also you can see this. This P should be identity. Yeah, what you're saying?
yeah, right. So the Venn diagram that you draw,
Hmm.
projectors uh, onto column space of A.
Hmm.
So does it also contain that projection vector U transpose
Obviously,
divided?
it is here, right? U transpose divided by U transpose U.
Okay, okay, right.
For all every other vector, you will have this projector, but for the vectors lying on this line, you will have identity matrix plus this projector. Fine.
Okay. So I was thinking what I was thinking about the other vacant spaces.
Hmm.
What other projectors could be possible for this, or are these the only two projectors that are in the Venn diagram, or there could be other
There are
projectors possible?
there can be infinite number of projectors depending upon the type of projection you are doing. But if you are doing orthogonal projection, there exists only one kind of projector, right?
Yeah. So suppose right now we are talking about only orthogonal projections.
Right. So
So
then
in
only
the Venn
this is
diagram,
only possible. Yeah.
okay, in the Venn diagram only identity projects the columns to itself, and that you transpose that thing.
Yeah. Yeah.
Okay, okay.
When you so very basically projection is very general term. So projection comes from the idea that, let's say you have a axis like this, and then you have some object or some, let's say, vector here. Then you project some light source from one direction, and then how will the shadow will be cast on that axis. Now you can cast the light shadow orthogonally such that the rays are perpendicular to the projection surface, or you may choose any other direction also, right? Oblique kind of
Okay,
projections.
right.
So you can have many possibilities in that case. That's why we are only considering the orthogonal case, right?
Okay.
So
Yes, sir.
let's move on to next question, right? Given an M, where is this question? Yeah. So suppose a matrix A is real M cross N matrix with rank N, and A dagger is its pseudo inverse. Which of the following properties is not always correct, right? So let's write is, yeah, so it says that rank is N. This means M is greater than N, right? So it's a tall matrix. So we can easily use the formula for pseudo inverse. So A dagger would be A transpose A whole inverse A transpose, right? So first one says option A. Let's try out the option A. It says
We can
A
add even
daggers.
greater than equal to n, right? Equal to also we can consider. So फिर it हो
You
गया.
can also consider equal to, in that case, it will become an inverse if it's a full rank, right? Yeah, which is full rank, yeah. Right. So it becomes A into A transpose A into A whole inverse A transpose A, right? Now you have this term. So A transpose A whole inverse into A transpose A will be identity. And this eventually will become A. So this is be true. This will be true always, right? Then option B, you can check A dagger. So which is A transpose A whole inverse, A transpose A, फिर A transpose A whole inverse, A transpose, right? This is right. So this essentially becomes this again, these two identity, and this is A dagger, right? So this is always true, always. Now A into A dagger. This is very straightforward problem, right? There is nothing to have issues, right? So you can simply expand this. So it becomes A inverse transpose into A transpose. These two becomes identity and it becomes A into A inverse, right? Can we say anything about A into A inverse? Will it be symmetric or not?
We can't use
We
the
can't
fact.
say.
We can't break the between parentheses A transpose A whole inverse. We can't write it as A inverse because
Acha,
we don't know A inverse will exist or not.
okay, right. You are right. Sorry. I assumed it to be a square matrix. Yeah, you're right.
We can
Right.
take the
So
transpose directly and we can see that the transpose is equal to itself. Another way to look at it is this is the projection matrix itself. So projection matrix is has to be symmetric because orthogonal projection we are considering.
Acha, this is basically projecting, right? This was the matrix that is essentially projecting the terms, right? A into A dagger, right? We don't need to think anything else from here.
Right.
Because it makes sense because what happens is uh, how to think of it? Um, A transpose A, and then I don't think you have studied anything related, anything that helps you to understand why it will be symmetric, right?
We can take directly the transpose of it. We have A dagger. We can take
Acha, right.
the
You can always
transpose
check
of it.
the. So we want to check if it's symmetric or not, right? Yeah. So what is the transpose of this term? The transpose would be a whole transpose, right? So A becomes here, and then the center term, which is A transpose A inverse transpose, which is already symmetric, so it becomes A transpose A inverse into A transpose. Yeah, so it's symmetric. It is true always. And then option D says it has to be identity. Let's see. No, it won't be identity always, right? Will it be? If A is square, then it will be identity. A inverse, inverse transpose, A transpose, and then it will be identity. Only if it is square, right? So not always true. True. So anyone, do you have any doubts in this problem?
No, sir. Got you.
Right. Next question, given an M crossing matrix, the pseudo inverse of a matrix with rank n, right? So again, M is greater than equals to n. So what is the formula for pseudo inverse?
A transpose the whole inverse into A transpose.
Option C, right? Any doubts? Right. So let's move on to the next question. Consider the matrix A of size 3 cross 7. So A is 3 by 7 matrix. The matrix that projects any vector B onto the column space of A is. Okay. Right. So, okay, let me think. We have A is a 3 cross 7 matrix. So basically 7 are 3 vectors, right? 7 are 3 vectors we have. So basically we want to project, so it's like this, consider it like this. You have 7 3-dimensional vectors. So V1, V2 up to V7, where which each Vi belongs to R7, I equals to 1 to 7, right?
R3, sir.
R3, right? R3, sorry. Yeah. And the question is, can we project any vector B R3 onto the column space of A, right? Yeah, column space of A. So column space of A is essentially R3. And are we given anything about the nullity of this? No, right? We don't know any other information. Now let's assume if the matrix is full rank, then you know the answer, right?
Uh,
Everyone, assuming if the
so
matrix is full rank.
then it will be identity matrix of size 3 by 3.
Yeah, right. So it will be identity matrix. Why? Because any three, there will be at
Right.
least there will be three basically identity. Why? Because there will be three linearly independent vectors, right? Column vectors that will span entire R3 space. And since any vector lies in R3, it will be the projector will be identity matrix, right? You don't need to do anything else. The matrix is itself. But now let's say you are not given any information, we cannot say, right? Now let's say if the matrix was singular, then you will identity matrix won't work, right? There will be that you will need additional information based on the type of matrix, so it is not computable in that sense. So option 5 is correct. If the question said it is full rank, then you don't have to think of anything, the identity matrix of size 3 by 3, right? Everyone, do you have any doubts?
No doubt, sir. Yeah.
Fine. Next question, the pseudo inverse for the matrix A is, do I need to solve this problem?
No, it will be option C.
Fine, thanks. Do you have any doubts? You can simply use the formula. A transpose A whole inverse A transpose, where A is basically minus 3, 4. So you know what will be A transpose. A transpose will be minus 3, 4. And then simply put it in the formula, you will get the answer, right? Let's move on to the next question. Suppose the characteristic equation of a 5 by 5 matrix A is given by this, then the determinant of A is.
A little bit
Anyone?
of typo is there. So lambda's power should be actually equal to 5, highest power. Option will be 0 only because one of the eigenvalues is 0, so determinant will be 0. But the characteristic equation can't be this because it's a cubic polynomial in lambda. So it has to be a something penta.
It will be lambda cube, no? So lambda cube, I think, so lambda cube means 0. It is repeating, no? That is.
Yeah.
Yeah, you
So
can. Yeah.
right, but yeah, we can always like put one of those things aside and say this is. But that will be a derived thing from the characteristic equation. That is not directly the characteristic equation because it need to have the power, the highest power as 5.
I mean, let's not get into the terminologies. Let's assume that this is lambda cube, right? Now everything is fine.
Okay. Right.
Right?
So
So option B is correct.
B will
Any doubt in this? Basically, you use the formulation that determinant is equals to product of eigenvalues. Do you know how to prove this?
I can try.
If the matrix is diagonalizable, then you can prove this.
All right. Then it will be
So
easier to prove.
yeah,
All right. So P and P inverse will get cancelled out.
yeah. Right, this is the proof. I think we already have done this. The determinant of a diagonal matrix is product of all the eigenvalues.
Right.
Fine. Anyone do you have any doubts in this?
No, sir.
So, sir,
Right.
in general, like even this statement is true for all matrices, right? Even which are not diagonalizable, still the determinant of them should be the product of the eigenvalues, right?
Yeah.
So, why doesn't any problem occur there? Or here I can easily think that determinant of P and the reciprocal, they get cancelled out. So only that thing is coming out very nicely. So let's consider a 2 by 2 matrix, which is not diagonalizable.
Okay.
And, uh, and I want to have the feeling that why the determinant is equal to the product of the eigenvalues.
So basically, you will be able to write it as PD. Sorry, AP equals to PD, right? And then you won't be able to take anything. Yes. Hmm. Let's think of this. So we will cover this maybe in today's session itself. There is a session there. You will learn more about eigenvalues after this problems also, right?
Okay, okay, right.
So let's question number 8. Suppose we are two orthogonal vectors in R5. The matrix that projects any vector onto the plane spanned by U and V is anyone? I think this was directly covered in the class, right? Which option is this? This is option
Option C. Option C. Option
C.
C.
C, right? This was, I think, covered in the lecture
Yeah.
itself, right?
Mhm.
Fine. So question number 9. Consider a system this for a solution to exist, we must have. So again, this was considered covered in the class, right?
Right, right.
And I also solved this,
Option A, yeah.
right? Everyone, do you
Yes.
have any doubts?
No, sir.
No, sir.
Question. Yeah. Last question, which is not a projection matrix. So you have to check only one property, P
Item
square
property.
equals to P, right?
C is
Which
failing that.
option? Huh?
C, option C is failing that. I think it will be zero matrix. Twice multiplying.
Right. So you just have to check if this is true. Otherwise, if P square not equals to P, it's not a projection matrix, right? So I think, yeah, we covered all the problems
Option
related to
option 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 A. Why it will be not correct?
what?
Question
A
number
is a
10.
projection matrix. Because identity matrix is a projection matrix, right?
What you're saying? Option you're
Option
saying
A.
why option A, why identity matrix is a projection matrix? That's your question, right?
No, no, because that is also applying, no? I square equal to I, and I
Right. So
transpose will be I.
yeah, right. So
So it will be projection matrix, no? That is the question, no?
the
Achha,
question
which
No,
is
of
the
them
which
is
is
question is
not
not
a
a
which is
projection?
not.
Okay.
right. Fine. So this was all for today's week 10's problems, right? Let me share this. Hmm. So, okay, fine. So this is done. So let's proceed with the this week's notes, right? Week 11 notes, and then right. So we already discussed in the previous session that there are some definitions, some terms known as eigenvalues and eigenvectors associated with matrices, and then there is a definition of diagonalizability, which is whatever you call it, right? Diagonalizability, that if a matrix is can be diagonalized, then it can be written as A equals to PD P inverse. Basically, eigenvalue decomposition exists, right? Now the question is how to check if it is a diagonalizable matrix, right? The first hint you might have got is, since we are considering only square matrices, do you remember how did we get this form? We wrote like this, something like this, right? AP equals to PD. Do you remember this form?
Right, right. Yeah,
Right, everyone?
right.
So the first hint on this diagonalizability comes from this equation itself. Can P be inverted? If P can be inverted, then you can write A equals to PD in P inverse. If it can't, then you can't write, right? So the criteria for a matrix to be diagonalizable is it must have, let's say if a matrix is n cross n matrix, then it must have n linearly independent eigenvectors. If there are n linearly independent eigenvectors, then you can write it as A equals to PDP inverse. The eigenvalue decomposition exists and it is a diagonalizable matrix, right? Second, this is clear, right? Point one is clear, everyone. Do you have any doubts?
Yes, sir. Yeah. No doubts, sir. Clear.
Now, for second point, geometric multiplicity. Do you remember geometric multiplicity?
Yes, sir.
right? Do you remember this thing here, right? So let's say you are talking about this characteristic equation. So let's say you have an n cross n matrix, right? So the characteristic equation would look like would something look like lambda alpha 1 lambda raised to power n, right? N, yeah, plus alpha 2 lambda raised to power n minus 1 plus dot 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 plus lambda n alpha and lambda raised for 0, right? So you will get this characteristic equations, p of lambda, right? P of lambda. And then lambda can be, now you solve this set of polynomials, roots solve for the root of this polynomial. And we all know that you may get imaginary roots, you may get real roots. If they are imaginary, they will occur in pairs, right? Conjugate pairs. If not, then you will get real roots. Then basically, if you get real roots, they can be repeated or distinct, right? Everyone, do you remember at least this part, right? So from here, we define algebraic multiplicity, which is am is equals to and note that these terms, whatever terms from now onwards I'm going to talk about, only considers one single eigenvalue of a an eigen value. What will be it? How many times it is present as a root of the characteristic equation, right? P lambda, right? So this is algebraic multiplicity. That's it, right? This is the definition of algebraic multiplicity. Then for each eigenvalue, then again, for each eigenvalue, right, you will have some eigenvectors, right? You will have a set of eigenvectors, right? What will be that set look like? It will look like, let's say I am considering an eigenvalue lambda I. So that set would be a null space of a minus lambda I, right? Null space of this matrix. Now, since this is a vector space, you can define the dimensionality of this vector space, right? Dimensionality and nullity, whatever, for this nullity of this matrix, which is dimensionality of basically eigenspace, right? Eigenspace. Now, right, you can always define this, and then you can define whatever the k number of linearly independent, k linearly independent eigenvectors that span this, right? That span this space, right? And you know that this space is also known as invariant subspace.
Because they don't go out of their line
Yeah,
because this.
right.
Oh,
Invariant subspace of lambda I. Why invariant subspace of lambda I? So let's say if a vector v belongs to null space of a minus lambda I, right? It is lambda I into identity matrix is here, right? Identity is here, right? Then we will see that AV will be equals to lambda V, right? So basically you are only scaling that vector. You are not changing the vector direction. So that's why it's also always so AV is lambda V. So you can say that AV belongs to null space of A minus lambda I into identity matrix. Now this is what makes it invariant subspace, right? So that's what it looks like. And then the number of linearly independent eigenvectors that span this space defines the geometric. Now this gives us the term geometric multiplicity, whatever, right? GM, right? So these are two basic definitions. Now my question is, what is the criteria for a matrix to be diagonalizable? That it must have at least, if it's n by n matrix, so it must have n linearly independent eigenvectors, right? Do you agree with this?
Yes, sir. Yeah. Right.
Right. So basically, sum of geometric multiplicity of all eigenvalues should be equals to n. And now this is one thing. The another thing is, now let's say your algebraic multiplicity is something for an eigenvalue AMI, right? Then that will be always greater than geometric multiplicity of that eigenvalue, right? And then if AMI is equals to GMI for all eigenvalues, then only it can be written as A equals to PD P inverse. Otherwise, if AMI is less greater than GMI for any I, the matrix would be is defective. So now these are the definitions. This can't be diagonalized, right? So these are the definitions that you need to remember. So I don't think there were some proofs given for it, right? Anyone, do you remember?
No, sir. This part that AM is greater than GM.
Yeah.
No, sir. Actually, there was no part. But yesterday, Professor Arul was taking the class. Like he took an live doubt solving session.
Yeah.
So in which he was mentioning something like this. So I asked for a intuitive proof for some kind of intuition.
Hmm.
So he was telling me something. So I
Hmm.
thought of giving it a try later, but I didn't till now. So I don't know the intuition behind it. I know the rigorous proof, how I can prove AM greater than GM,
Hmm.
but why intuitively? And I feel that intuition should be quite natural. Like uh, suppose some lambda is repeating too many times, only two times. Let's say lambda equal to 3, 3, then there can't be more than two linearly independent eigenvector in it. But I'm having the feeling, but I'm not able to express it. So, what is your thought on this? If something repeats, let's say 5 times, then why can't we have more than five linearly independent eigenvectors in it?
So essentially, everything boils down to how you look at the characteristic equation, right? So if you have
Right.
repeated roots, so can you think of what it looks like, what it would look like? Like how will this characteristic equation look like? And then from there you can build up like what should be the why the AM should be greater than equals to GM. So it comes from there, but yeah, it will take time. You think about this and you will get to this. Um, the rigorous proofs are given, but getting an intuition, yeah, it will take time. Like you will have to think of it more.
So from characteristic equation, eigenvalues repetition and that nature could be found out. But
Hmm.
the geometric multiplicity, which essentially connects with the null space of A minus lambda I, can we look at it? Can we look at the geometric multiplicity from the characteristic equations, or characteristic equation reveals nothing about the geometric multiplicity?
No, it does not give you any information on the, it gives you an upper bound only.
No, actually, that's what I'm trying to say. So if I don't know that
Hmm.
aim is the upper bound, then
Hmm.
characteristic equation, can we infer anything from the characteristic equation about the geometric multiplicity, given that we don't know aim greater than gm?
Okay, so let's say I have this matrix, right? And
Right.
I want to think about the null space of this matrix. Hmm. So think of this. A is a matrix like this. So A का something like this. I'm using AX equals to lambda. So let's think of it like this. So whenever I'm defining eigenvector, I say AX equals to lambda x, right?
Right.
Now, when you say, let's say matrix A has some eigenvectors, we don't know yet, and we just know this definition that Ax equals to lambda x. Now let's choose one of the eigenvalues, right? And I'm
Right.
saying Ax equals to lambda x, lambda I x, right? Now let's choose another vector y, which is not dependent on x, Ay equals to lambda Iy. This is what I'm saying, right? This is what it looks like. So essentially, uh, now let me go down the page. Right. So now Ay equals to lambda Iy, and then I want to think of A minus lambda I into identity, and what the null space of this matrix look like? What does the determinant of this matrix look like, right? Now, if you have one dimensional null space, right? So what can you say anything about this is um right. So then you will say that see that all the like two eigenvalues cannot map to the same eigenvector, right? We have proven this, right? A lambda
Right. Right.
I
Exactly.
Ax equals to lambda 1x and Ay equals to lambda 2y, sorry, lambda 1y, right? Where x is not related to y, I mean not in the direction of y, then you will see that such a lambda cannot exist, right? Do we agree with this?
Um.
Like x has to be equals to y for this case, right? Do we agree with
Uh,
this?
no, actually, if the lambdas were different, if we say that in the later case, Ax equal to lambda 2x, then I could have
Mhm.
argued that lambda must be same for the same eigenvector. But for the same eigenvalue, two linearly independent eigenvectors can appear, no? And that's why geometric multiplicity is occurring.
Okay, yeah, right. I was doing opposite.
So initially, what you are writing, that was right, that Ax equal to lambda 1x and Ax equal to lambda 2x.
Hmm. And then Ax equals to lambda 2x. And in that sense, you need
Yeah,
the eigen sorry, lambda 1 has to be equals to
equal to,
lambda 2, right? If x is not 0,
right.
right?
And that is by the
Now,
definition of eigenvector, x is non-zero.
yeah, right. Now think of it like this. So when you try to solve this, get the root of this characteristic equation, you are getting lambda 1 and lambda 2. And what can you say about the behavior of Ax equals to lambda x, right? Now, what can you say if it's a space span, right? X1, X2, and this is a space, and you're trying to figure out the geometric multiplicity of this, and why you want to give some intuition on why there is a bound on here, right? So why lambda should come two times, okay? I don't think there is some straightforward intuition. So let me check. So did you get something from here, like from the idea, what the
Uh,
professor told you?
so, not really actually. So, what he guided me uh, circularly, it assumes that AM greater than GM. So, initially, I was thinking that okay, it will lead me to a very nice thing. But later on, I figured that it was quite circular answer. Like in some point, we are assuming that. Uh, so basically, we are using the same fact in its proof at some point.
Acha, right.
Uh,
Okay, so yeah, but what I am thinking of is, let's say you have some eigenvalue, and then
mhm.
you are stretching in two different directions, and both are in both direction the thing is stretched in by same amount. The vector is getting stretched by same amount, right? Then this means the what happens to the correct roots of the characteristic equations, right? Because you cannot say anything just by saying the characteristic equation. You need to look at the roots of that characteristic equation, and that is not straightforward to uh, think intuitively for this eigenvalue, right?
Right.
Hmm. What will be the total number of roots that we will get for the maximum total number of roots will be total
That will be n.
roots will be
So
n, right?
correct.
Either repeated or not, and either repeated or not, and let's say so let's call it 3 by 3 system, and then three roots are there, and I'm saying let's try to build up some contradiction. If the geometric multiplicity with one of the eigenvalue is, let's say, one, let's say three distinct real roots, so 1, 2,
Okay,
and
okay.
3, and let's say so GM is always 1 for all of these. For one, let's say now it's a 3 by 3 matrix, right? So it can stretch in X, Y, or Z direction.
Right.
Now let's assume yeah, right. So now you have different eigenvalues for different spaces. So it essentially looks like this: 1, 2, 3. Let's call this matrix. Right. Now what I'm saying is 3 has the first one associated with the first eigenvalue. I have two eigenvectors. Is this possible? Hmm. Hmm, hmm, hmm.
Yeah, this method of contradiction seems nice actually. So let me get you, sir. So you are
Hmm,
saying that total number of roots is n, right? And you are
hmm,
saying the total number of maximum number of linearly independent eigenvector for
hmm,
this n by n matrix can also
hmm.
be n.
Right, that's true,
So
because it's n
if
by n space. So for
right,
any kind of matrix,
right.
yeah.
So now you are trying to uh, now you are trying to assume that geometric multiplicity is more than algebraic multiplicity for a particular case, and
Right.
see whether that brings any contradiction or not, right? This is what you are
Yeah,
trying to do.
yeah.
Okay, so
So
if we allocate,
huh.
sorry, go on.
So I think we should discuss this in the next session. Just try on this idea if you get
Okay,
somewhere,
okay, sure.
right? Because I need to cover up
Yeah,
other problems also, right?
yes, sir.
So,
Yeah,
so let's discuss this. Just remind me in the next session, right?
sure, sir.
So till now everything is clear, right? So now we know the definition of defective matrix. Then we know, let's do something for real symmetric matrices. I'm going really fast, so just stop me if you have any doubts, right?
Okay,
So
sir.
now we are we are discussing an n cross n real symmetric matrix. That is A transpose at A, and all the entries of the matrix are real numbers, right? So it is A is R. A belongs to real space R n cross n, right? Now then A inverse is also symmetric. Can we prove this, everyone? Any doubts?
If it exists, right?
It's a full rank n cross n real symmetric matrix,
Okay, okay. Yes,
right?
right.
Let's put it here, full rank also. So it will be symmetric. Anyone, if you have any doubt, please ask me. Then what are the eigenvalues? So what you do, you simply write the characteristic equation for, let's say, 3 by 3 matrix, and you will observe that for 2 by 2 matrix, you will observe that in the quadratic equation, you will see that always real roots exist. So this is for just for 2 by 2 case, which is very easy to prove, but this can be proven for general cases also, as we will see in the next in the further points, right? So it is clear for 2 by 2 case, right?
Yes, sir. Yeah.
Right. Now A into A transpose and A transpose A are also real and symmetric. This is very simple. So real, proving that they are real, it's very easy because you are simply doing matrix product. So if the inputs are real, the outputs will always be real, right? Because you're not taking any square roots or anything that will give you imaginary values, so they will be real. Then for symmetric, you can simply check if B transpose equals to B, and you will see that these two will also be symmetric, real and symmetric, right? Then eigenvectors associated with distinct eigenvalues, if A is a square symmetric matrix, eigenvectors will be perpendicular. They will form orthogonal space. Is this point clear? So here's a proof also. If you have doubt, then I will go into depth for this. Is this clear, everyone?
Yes, sir.
So let's say if you have a real symmetric matrix A, n cross n. Now what I'm saying is, if let's say you have eigenvalue lambda 1 and eigenvalue lambda 2, and eigenvalue lambda 1 considers eigenvectors ev1 and ev2, and lambda 2 contains ev3, then ev1 EV2 will be orthogonal to perpendicular to EV3. So this is what this is claiming, and this is how you prove this. Do you have any doubts on this? This has been covered in the class, I guess.
Right, sir. But we can't say anything about EV1 and EV2, right? Which are coming from the same eigenspace.
Yeah, they may or may not be orthogonal. Yeah.
Okay, okay.
Right.
Yeah.
So eigenvalues of real symmetric matrix are real, right? So now we have to show that the eigenvalues of real symmetric matrix are real. For this, you can prove this. How to say this, right? This point. Very simple. Just assume that the eigenvalue is an imaginary value. So it's a complex number, a plus iota b. Then its Hermitian part. Hermitian is essentially complex conjugate, which is a minus iota b. Now you know the definition of eigenvalue decomposition. Eigenvalue, which is au is sorry, au equals to lambda u, or a u Hermitian equals to lambda Hermitian u Hermitian, right? So this is how you extend to imaginary matrices with complex values. And then using that property, you can show that you will see that lambda will be equals to lambda Hermitian. And this only exists for real lambda values, real values only, right? Anyone do you have any doubts for this?
Sir, can you just give a recall of what Hermitian is, like for a matrix?
Sorry, there are two things. So one is complex conjugate and one is Hermitian. These are two different terms. So if you have a real number, a lambda, let's say, so let's say if you have a real number in R1, then star means complex conjugate. This is clear, right? Sorry, no, a scalar, not R1, a complex one, C1, right? A C1, for C1 value, any value belongs to C1, this star will indicate complex conjugate. This is clear, right?
Yes, sir. Yeah.
Now for complex matrices, there is a term known as Hermitian. So what it does, it is essentially a substitute for A transpose, right? For complex values. And in A transpose, what happens? First you do simple A transpose operation and then replace all complex entries with conjugates. So this is what this will give you the Hermitian of a matrix. Fine.
Yep.
Is this clear?
Yeah. Yes, sir. Yeah.
So whenever you do transpose operation on a complex matrix, you use the Hermitian operator,
Right. Yes.
right? Using this, can you figure out the proof here, everyone? This is very straightforward. You don't need to think of anything else. Now, for us, complex number, if you say lambda Hermitian is equals to lambda, what does this mean? A plus iota b equals to a minus iota b, right? This means a equals to a and b equals to minus b. For what value a b equals to minus b? For what scalar value you get a value equals to minus value? What is the number? Anyone?
0.
0, right? So b has to be 0. This means a lambda has to be a, and a means it's a real number. That's what we are trying to prove here, right? Now, spectral theorem, right? Now let's say if I can, A is real and symmetric. We have shown that for distinct eigenvalues, you get orthogonal eigenvectors, right? Fine. Now, if A is, let's say A is a symmetric matrix that can be written as PDP inverse, right? That we have already seen. Then what is A into X? What happens when you multiply that matrix with a vector? So you can simply write it as PDP inverse into X, right? Is this clear, everyone?
Yes, sir. Yeah.
Fine. Now you will observe that for eigenvalues, for real symmetric matrices, the eigenvectors form orthogonal set, right? That we already saw, right? Where was this? This we saw, right? P equals to, inverse of P will be P transpose. Is this clear? Was this covered in the class?
Yes, I think so.
Right? So you can always write this PDP inverse as PDP transpose, since P is an orthogonal matrix. And then from there, you can say lambda 1 into U transpose by, basically now what you are doing is Right. Hmm. Okay. Now what you do, you just expand this product PDP transpose into X. And let's say it was a 2 by 2 matrix for 2 by 2 matrix. And let's say your P matrix contained the elements U and V as its column vectors, right? P is essentially U, the first eigenvector, and V as the second eigenvector, right? Then you will observe that PDP X transpose X will be equivalent to, and then T is essentially lambda 1 and lambda 2, right? So then you will, when you do this product, matrix vector product, matrix matrix and matrix vector product, you will observe that this will result in this quantity lambda 1 into UU transpose by U transpose U into X plus lambda 2 into VV transpose by V transpose V into X, right? Do you remember these terms? Anyone?
Yes, sir. In the just few minutes back in the assignment also, in the
Yeah.
problem statement also we saw this.
So we are essentially what we are doing, we are projecting the vector X into the eigenspace of A, right? Into the space of eigenvectors of A, right? Now this brings us to the spectral theorem for real symmetric matrices, right? Real symmetric matrices, right? Uh, there will be n real eigenvalues. We already saw the proof, right? I hope you know. Then you will see that algebraic multiplicity and geometric multiplicity will be same. Now, why I'm saying this? Why is this true? You can think of it like this. I'm saying is the matrix P, which contains the eigenvectors, is orthogonal matrix, right? This means all the eigenvectors are orthogonal. This means the number of you don't need to think anything. You just have to think of if it is diagonalizable or not. If you can prove that, then you will see that this is true, right? Then eigenvectors corresponding to distinct eigenvalues are perpendicular, that we already saw here using this proof. I think where was the proof? This was the proof, right? Eigenvectors associated with distinct eigenvalues values are perpendicular. And then A is orthogonally diagonalizable. Why? Because the matrix P will be orthogonal. That's why we are saying this. Matrix P will be orthogonal. That's why we are saying A is orthogonally diagonalizable. Anyone, do you have any doubts?
No, sir. Sir,
Right?
so when just one thing. So when we say that A is orthogonally diagonalizable, so
Mhm.
if repetition is not occurring, then it's very good.
Yeah.
They are all already automatically perpendicular. And
Mhm.
my doubt is in this case that if repetition arises,
Mhm.
so then they are suggesting that okay, then you perform Gram-Schmidt and you are getting
Mhm.
orthogonal vectors. But
Yeah.
performing Gram-Schmidt, they don't interfere the eigenvalues. Like when I have two vectors, I'm doing Gram-Schmidt.
Yeah.
So I'm making them orthogonal, that's fine. But is it like, are they still becoming eigenvectors while
Okay,
doing?
so yeah, right. Okay, fine. So are they still the eigenvectors, right? Hmm. Uh, o- Let me think of this. What? Hmm. Okay, how can we think of this? Is so. Mhm. Yeah, there was this. Right. Yeah, right. So what happens is actually what, right? So again, when you have this system, right, A minus lambda I, and you are looking at the null space of this thing, right? And we know that AM equals to GM for this real symmetric matrices, right? Then what I'm saying is GM is the space, null dimensionality of this space, right? Nullity of this, nullity of A minus lambda I, and that will be a space, right? So in this space, you can always choose two orthogonal vectors, right? N, sorry, basically N minus K orthogonal vectors, always, right? Where N minus K is basically nullity of A minus lambda I, right?
Okay, right. So they are still in that plane, and just because that invariant subspace. So okay. Right, right, right. So they are indeed eigenvectors.
Yeah. So this is it, right? So A can be orthogonally diagonalizable. That if that is not direct, you can always convert that decomposition into orthogonal decomposition, right? Then what the spectral decomposition says, again, we saw this in option this earlier, that if it has two eigenvectors, you will observe this. For n eigenvectors, you will observe this. If it's n across n matrix, you can write A into X, a matrix vector product, as a linear combination of projections of that vector along the eigenvectors of that matrix for that real symmetric matrix, right? So this is your spectral theorem. Fine,
Sir,
everyone?
is this UI and UI transpose or UI into VI transpose?
UI into UI transpose. UI into VI transpose. They are ortho. So UI into UI transpose. This
Okay,
is,
okay, right, right. Mm-hmm.
and you are assuming here that UI is basically unit matrix, unit vector, right?
Right,
Otherwise, you
right.
will require UI
Yes, yes.
transpose. Fine. Now, the last topic that we need to cover is the quadratic forms, right? For why we are everything is clear related to eigenvalues and spectral theorem, right?
Yes, sir. Till now, this is clear.
Right. Now, let's move on to the last topic, which is uh, sorry. Right. Then what is quadratic form? Now, for quadratic form, why it is useful, that I can tell you. So basically, do you remember the LU decomposition part that we were seeing? LU decomposition. Anyone, do you remember this?
Yes, sir. Yeah.
Why we were doing this?
So it reduces computational complexity
Right.
for
So
any kind
basically,
of B. Yeah.
right. If you are trying to solve this system of equations Ax equals to y, you can write it as Lux equals to y. And since L is it's very simple to do the inverse of a lower triangular matrix, you can always solve this as Ux equals to L inverse y. And now this is simply back substitution. So you will get a upper triangular matrix, and you simply do back substitutions, and you will get the solution in numerically efficient way. Right, everyone?
Yes, sir. Yeah.
Do you remember this? Right. Now there is another interesting decomposition, Cholesky decomposition, right? That you will see. Now what it does is it does some sort of factorization that looks like this. The benefits are, if the matrix is symmetric, and additionally there is one more constraint that we are going to see using these quadratic forms. If these two conditions are satisfied for a matrix, if the square matrix and symmetric, then the Cholesky decomposition is really faster than LU decomposition. And again, a Cholesky decomposition allows you to do this kind of solution, allows you to solve Ax equals to y very fast, right? So first thing what we did, we improved the speed up. We improved the throughput of LU factorization by replacing the LU to by Cholesky decomposition. That we will be able to do if the special properties are satisfied. And then if we are able to do that decomposition, the solve will be faster, right? So that's why we are going to learn this quadratic form, what it means. This is an overall idea, right? So this was some intuition of why we are going to see these things. Fine.
Excuse me, sir. Like what Cholesky decomposition you have said, is it SVD?
No. It's different from SVD.
Okay.
SVD is the most powerful form of decomposition that essentially exists, but it is the more. It is very slow.
Sir, Chori's case is that, no, like where we take square root of for matrix things, like it's
Yeah,
kind of a
we will see in the later
okay, okay.
lectures, right? So let's start with the quadratic forms. So essentially, let's say I have a matrix that is a symmetric matrix with four entries A, B, B, C, with four entries as A, B, B, C. It's a symmetric matrix, right? Now, and let's say I have a vector X. So let's say the matrix A is n cross n, and X, the vector X is n cross 1 always, right? So you can get this set of matrix and vector, right? Then what is a quadratic form? Quadratic form is an equation that is given as X transpose AX. This is the definition of a quadratic form. Is this clear? So you
Yes.
simply expand X transpose AX and you will get the quadratic form. It's a scalar value that gives you some information of a matrix, right? Is this clear?
Yes, yeah.
Fine. So right. Then I have given you the definition of a quadratic form, and then from there we can build upon the principal axis theorem, right? Now, if you are given a square matrix which is symmetric and real, right? Then we have an orthogonal change of variables. Let's say we have then we have an orthogonal change of variables x equals to py that transform the quadratic form with no cross terms, right? So this is something that comes from the uh, uh, this comes from the spectral theorem itself, right? How it is coming, you can look at the proof. So it's very simple. Let's say I'm defining another form q of x1 x2, right? It is given as x transpose ax. Now I'm saying x is an orthogonal projection of another vector y by a matrix p, x equals to py, right everyone?
Yes.
So now tell me if you miss something here, right? So now x is py, let's say. So it's projection of some other vector y on some plane, right? Now what you do, you replace x by py and you rearrange the terms. You will get this y transpose p transpose apy is equals to x transpose ax, right? Now just look at the central part, which is p transpose ap. Do you remember this?
Yes, it's diagonalization. If we take P to be the eigenvectors,
Right, but A is not diagonal, right?
so it will make a diagonal, right? Uh, if A is
What is it?
diagonalizable, so
Yeah,
A is
A is
diagonalizable.
diagonalizable, right? Yeah.
So
So
if we choose
we remember this, right? P AP equals to P into D, right? You remember this, everyone,
right, right, yeah,
right? So we are just looking at the central part, right? P transpose AP, and trying to figure out what it means. So we know that if A is real and symmetric matrix, real symmetric square matrix, you can write it as AP equals to PD, where A equals to PD P transpose. Or you can say that T equals to P transpose AP, right? Everyone, do you agree with this? Right. So now from here, you can say that X transpose, this X transpose AX is essentially Y transpose DY, right? Now, Y transpose DIY, what is this? You simply expand it, right? Y transpose DY. X transpose AX is essentially just expand it and you will see that it will be Y transpose dy will be some positive quantity always, right? Is this clear,
yes,
everyone?
yes, yeah,
I haven't done anything. I am just stating something. I'm just proving, just showing that this is possible if this is the case, right? I haven't done anything till now. After this, I will define some terms and it will depend on the properties of the matrix, right? Now, let's this is the principal axis theorem that transforms the quadratic form if we can have an orthogonal change of variables, so basically x can be transformed with py that transform the quadratic form with no cross terms, which is y1 d1 squared plus y2 d2 squared. Basically, you can transform the form into some sort of new form, right? Now, this was this about principal axis theorem. Now, the base important definitions that we get from this quadratic form that I was discussing, right? That we need from here, right? Now, if you have a quadratic form, if you have a quadratic form of x1 comma x2 given as x transpose ax, then if x transpose ax is greater than 0, the matrix A for all vectors x, for all x, right? Then the matrix A is said to be positive definite, right? Now, if x transpose ax is less than 0, it is said to be negative definite. If x transpose ax is positive for some x and x transpose ax is less than 0 for some x, then it is indefinite. And then again, if you apply equality also here, x transpose ax greater than equals to 0, then positive semi-definite. And x transpose ax is less than equals to 0, then it is positive, negative semi-definite, right? So these are the basics for this. Just remember the equations, these rules. That's it, right? Now, another thing, x transpose ax is positive definite is of all the eigenvalues are positive, negative definite if all the eigenvalues are negative, and then again, semi-definite, negative semi-definite, and indefinite rules follow similarly, right? Everyone, is this clear?
Yes, sir.
Now, get the proof like why this depends on the values of eigenvalues? Anyone? If A
Uh,
is real symmetric matrix.
right. We can expand and see that how the form will look like.
Yeah. So it is essentially P transpose X, right? So P is U, let's call this V, right, into X1, X2, right? So this is U dot X1, U dot X2, right? And then you multiply it with the diagonal matrix. So, so it becomes a diagonal matrix with these entries, right? So just multiply and see what it looks like. U dot X1, V dot X2, right? Now again, you multiply it with P transpose X into D into P. Again, you multiply with U, then V. Oh, sorry. U here and then V here. And do the multi product again. So AQ1 will be U into this, right? And then multiply with X transpose. You will observe that this sum will become some linear combination of all the eigenvalues. And then from there, you can see that it is positive if and only if all the eigenvalues are greater than 0. Fine, everyone?
Right. Yes, sir. And
So it
the
will become
coefficients are
something like
coming out to
this,
be
xi square into lambda I, something like
right.
this,
Right. Yes.
right?
Yeah.
So now these are positive values. So if it is, if all the if it is positive definite or not, entirely depends on lambda eigenvalues.
Right.
So anyone, do you have
Yes,
any
sir.
doubts in this definitions?
No, sir.
Fine. Right. So now this was all that was covered till week 11. So let's solve few problems on week 11 session, and then we can end the session, right? It's PDF. Yes. Okay. Just share. Share. Right. So let's solve few problems on this and then we can end the session. So let lambda 1, lambda 2 will be the eigenvalues of a matrix A for A R2 R2. Then a geometric multiplicity, GM is the geometric multiplicity of an eigenvalue lambda. Then few questions. Can you solve this, everyone? You know how to solve this, right?
Right. A is wrong. The trace is 3.
Right? Now you set the determinant of this matrix to 0 and solve for lambda. Minus 25 equals to 0. So have you solved this? Anyone, do you have the answer for this? I think this is the first time you are saying this, right?
Just give us 1 minute.
2 plus 1, 3, and plus 2 is 25. 0. And then from here you can figure out what will be the lambda, right? What is the answer?
Yes, I'm trying. Yes.
Yeah, what?
Yeah, yes, I'm trying. So I'm solving it actually.
Okay, so one thing we can figure out, right? We can figure out one thing. So b square minus 4ac is non-zero, right? Plus 4 into 23, right? So basically you will get two real and distinct eigenvalues, right? Now what we can say, if the 2 by 2 matrix and we have two real and distinct matrices, eigenvalues, we can say algebraic multiplicity is 1 for, right, everyone? Don't need to solve anything other from further from here for lambda
Right.
1 and
Yeah.
lambda 2, right? And then since it's a full rank matrix, right? It is a full
Right.
rank. So you have gm equals to 1 for lambda 1 equals to lambda 1 and lambda 2, right? Am I missing something?
No, sir.
Right? Now the
Yeah, right.
question is lambda 1 by 2 plus lambda 2 by 2 is 2.5. You can solve this equation and get the value. Check what is the answer. Is A
You can
defective? No.
see the trace.
Yeah.
And look at the trace and it is wrong. So lambda 1 plus lambda 2 should be 3. The
Option
trace
one
says
is wrong. Option one is wrong.
Hmm.
Option
option D
one
should
is
be the
wrong.
correct answer.
Option B is also wrong because geometry multiplicities are 1, 1 each. So
Right, right. So
option D
D is
should be
correct.
correct. D is correct, right?
Yeah. 1.5 plus 2 is equal to
Ah,
3.5.
right. Fine. So option D is correct. Right. So question number 2. Consider the 2 by 2 matrix with eigenvalues lambda 1 as this, lambda 2 as this, then A is. Anyone?
Uh, yeah. So one of the eigenvalues is positive, another is negative. So it should be indefinite.
Right. Option D. Any doubts?
No.
Fine. Question number 3. If A is a 7 by 3 matrix of rank 3, then the number of singular values of A which are 0. Number of singular value decomposition is covered or not? Till week 11.
I haven't. So I haven't gone through all the videos of week 11. So I'm not sure. Satinder, can you confirm SVD is done or not
No, as
in week
far as
11?
I think
In week
I
12, I
think
think it will be covered.
uh, in
it's
12th it
not
will be
covered
correct.
in the notes because I am following the
Hmm.
notes
Oh,
itself.
right,
So it's not covered in the notes as far as I know.
No, no.
right.
Right. So let's keep this problem for next time, right? Question number 4, very big problem. Yeah. Right. The eigenvalues of matrix A are this and this. The corresponding eigenvectors are something. Let X be a 2D real vector that such that its projection on U is this and its projection on V is this. Then AX is. Anyone?
So X is already written as two parts. So we'll use that fact and the eigenvector property that.
You can use a
So,
spectral theorem, right?
oh yes, right. Spectral theorem also we can use.
If A is a real symmetric matrix, you just have to check that U dot V is 0 or not. Is this true? Then we can use this. Then
Yes, it is.
we can use this, right?
Right, they are 0.
So this is 0, right?
Yes, 2 dot b, no?
Hmm. So it will be 1 by 100 into
B.
minus 1 plus root 101 minus 1 minus, so a square minus b square. So it will be 1 by
Yeah.
100 into
Right.
1
So it is minus 1 plus 1,
minus
0.
101, right? So it will be minus 1. It will be 0, right? So then we can use this spectral theorem, right?
Mm-hmm.
So can you give me the answer?
Yes, sir, in a minute. X is this. Lambda. Okay.
Ax equals to 3 plus 101 half 3 plus 3 minus. Option D is correct,
Oh, right, right. Yeah.
right?
Yeah.
Any doubts?
No, sir.
Anyone? Fine. Now, question number 4. Which of the following is not true about projection matrices?
In general, they are not symmetric, but this was one of the problem that I was asking, sir. So
Hmm.
he told that we only taught you about orthogonal projections. So you should not be so you should not be thinking about any other projections. But they are invertible is false, as well as uh, their symmetric is also false, because at some
Not,
time they might not be.
yeah, right. Fine. Yeah, that's true even, yeah. Let's consider orthogonal. Let me reduce the set. Then it's fine, right? They can be
Then
non-invertible,
A
right?
can also be A can also be not true, right?
They are rank deficient. They can or cannot be.
Right. So it is
No,
not
they
as
have
if
to be
they are
rank
always
deficient.
rank deficient.
They are always rank deficient, right?
What if I consider identity matrix as projection matrix?
They are always rank deficient because U transpose is a rank deficient matrix. And UU transpose, but UU transpose plus VV transpose might be full rank,
Right.
right?
Right.
Uh, yeah, you're right. They may or may not be rank deficient.
Right. So symmetric and idempotent are guaranteed for orthogonal projections, but
Hmm.
we can't guarantee anything about rank deficient or invertible. Actually, one satisfies the other. When we are saying that they are not always invertible, that means they are not always rank
Right,
deficient.
right. If they are not invertible, then they have to be rank deficient, right?
Right. Yeah.
Let's think.
Excuse me, here I have a doubt, sir.
Yeah, yeah, yeah.
Are they talking about the projection matrices formed by the your eigenvector, or just for a general case?
General projection matrix.
So general projection will be that A transpose A inverse and A transpose. That will be projection matrix. That part.
Right. That is a kind of projection matrix. Yeah, that's true. But that is not a square matrix, so we can't talk about invertibility. But the thing is, they have to be rank deficient. All the, matlab, all the projection matrix has to be
Like if it is
rank
if it
deficient.
is a column rank, it may be full column matrix also, like overdetermined and underdetermined. For that also, though, it is not necessary that it should be rank deficient. In that also, we take the projection matrix to solve, I think, for overdetermined and underdetermined things.
What you're saying?
I'm saying ki if the matrix is 4 cross 7,
Hmm.
so it is full rank and it is full rank, then also we can take the projection matrix and we can solve, no?
So 4
So
cross
it is
7
not.
case is something that we haven't covered, right?
No, I'm saying I'm just taking a general example. Or if I'm going to take 3 cross 2 and it is a full rank matrix,
Okay.
so that in that case also we can take the projection matrix.
Hmm. So what is the definition of a projection matrix, right?
Like so,
So it's basically like for projection matrix, the only property is important is idempotent. If it is orthogonal projection, then it is symmetric, right? But let's say if the matrix is full rank, then all the vectors lie in its space until and unless it's a rectangular matrix, right? Now, basically, if a matrix is full rank, then the project and it's a square, then the projection is nothing but the identity matrix. But since we are not dealing with that, they have to be rank deficient. Why they have to be rank deficient? Right. I don't think there is some theorem on that. So let me check. Projection is be rank deficient. Okay. So let me just check and confirm, because the only property you need to think of is when you think of projectors is idempotent property.
hello, excuse me, sir.
Yeah, right. So it has to be rank deficient except for the identity matrix. So that is,
Like
yeah.
just one example you can see 1001
Hmm.
column wise I'm telling.
Yeah.
Then second column is 0101
Hmm.
and third column is 0011.
Hmm. Yeah.
So it will be rank deficit.
It's a full rank matrix, right?
This one is full rank, but the projection matrix which projects onto the column space of A. So we have only 3 linear independent columns,
Hmm.
and the whole vector is R4.
Right.
So basically, it will project a smaller
R4
version of
into R
R4.
R3, right?
Right.
So it will be a rank deficient. Then projection will be a rank deficient matrix. You are right. Yeah. So basically, when you think of the you are trying to project something onto the column space of A, you don't look at the A, you look at the term pseudo inverse, right? If it exists, A transpose A inverse, A whole transpose. Is this full rank or not? Right. So that's where the doubt is coming from. So A might be full rank, but the projection onto its column space might not, will not be. That's what I'm claiming. Right? Is this clear, Satinder?
Right. So one thing can we surely say that the rank of the projection matrix is equal to the dimension of the column space of the space we are projecting on.
Yeah, obviously, yeah, that's true.
So only except the case when we are projecting on the whole space. In excepting this case, all other cases projection matrices are rank deficient. Rank deficient.
Yeah, except identity. You're right, yeah. So if it's rank deficient, basically if you are doing some sort of projection, then what you're doing? you are collapsing in one of the directions, right? You are removing a part of the matrix, making that component to be zero, the component which is orthogonal to the plane of projection, right? That's what you're always
Correct.
doing. Then think of it like this. Then let's say you have a matrix that contains that spans entire space. Since you are essentially doing matrix multiplication in that space, right? Then it has to be rank deficient, otherwise you will get some component in the normal direction. So you can think of it like that also.
Right. Right.
Is it clear?
Yeah. Yeah.
Right, basically you have a matrix that can also contain this space, but then it won't be a projection onto this space. For it to be a projection onto this space, this space has to be as null space of that projection matrix, right?
Right.
Basically AB projected part, sorry, AB equals to P, then yeah, you are having some null space of A. You have to be have some null space,
Mhm.
otherwise you won't be projecting to anything.
Right. Right.
Right. Question number 6. Consider the real matrix this such that A is R3 equal to 3. Then lambda be an eigenvalue. AM, AM and GM are known, right? Anyone, can you give me the answer for this?
So all the eigenvalues seem to be zero. And A is not algebraic multiplicity and GM is
Lambda
zero.
cube, lambda into, right? This minus this is 0. It's 1 into this, right? This is a singular matrix, right? And
This
it's
is a
not,
singular matrix. Yeah.
is it
All the
diagonalizable?
eigenvalues are zero. Zero repeats three times.
Yeah, right.
And the eigenspace only considers two
No, no, no,
vectors,
no,
this
no.
two
All
columns.
the eigenvalues are non-zero, right?
No, all is zero, right? There is a diagonal triangular matrix. Determinant is zero, trace is zero.
Okay. No, at least one, some of the eigenvalues is also zero, right? No, what I'm saying is if all the eigenvalues are zero, then you writing P zero matrix and P inverse is equals to, and it's not diagonalizable, right? You can't write, basically, if all the eigenvalues are zero and then P, D, and P inverse will be zero, right? If this is zero. That says A equals to 0 if you want to write it as A equals to PDP inverse, right? This means A is not equals to PDP inverse. It's not
Diagonalizable.
diagonalizable, which means GM is less than AM, at least for one eigenvalue, right?
So we can also see exactly what is GM. GM is exactly 2 and AM is 3 for 0, right? From here.
Yeah, right.
Yes, sir.
So basically 0 comes 3 times and you are spanning two-dimensional null space. So
Right.
anything else in this?
No, sir, rest of the things are false.
Right. So let's move on to the next question. Consider the matrix A. A is positive, semi-definite, negative definite, or indefinite. Again, what are the
Semi-definite.
eigenvalues? 1
1
and
and
0,
0.
right? So what is the answer?
Positive semi-definite.
Right. Look at the eigenvalues. Right. Now let's move on to the next question. Statement question number 8. Right, you are informed, right, the one is matrix 1 is 1 1 1 1, it is defective, the second one is defective, and we have to check which one is true, right?
So what do you mean by defective? Rank deficient.
Your defective matrix is matrix where AM is greater than GM, right?
Okay.
It cannot be diagonalized, that's the question.
Okay. Okay.
So how can we check?
So we can, for the first matrix, eigenvalues are
So it will be lambda minus 1 into lambda minus 1 equals to 0. So you get lambda square minus lambda minus 1 equals to 0, right? Can we
right.
get the answer for this?
Yes.
Right. Am I right here?
Right.
B square minus 4c plus 4, right? So this is 1 plus minus root 5 by 2.
Right. So two distinct eigenvalues.
We have two distinct eigenvalues, right?
So GM will be 2 here. So it will not be defective.
GM is, sorry, AM is always 1, right? 1 for both.
Yeah.
Right?
And GM must be 1. So GM has to be greater than 0.
GM has to be 1 for both. So it is non-defective, right? So option statement 1 is false, right?
Yeah.
Let's think of the second matrix 0, 1, 1, 1, 0, 1, 1, 1, right?
This is
So
defective.
again, it will be minus lambda into, so lambda into lambda minus 1.
Sir, did we write the matrix wrong? Like, can you?
That's a 1, 1, 1,
1,
1.
1.
That's what I was thinking. 1, 1, 0, 1.
Yeah. 1, 0.
1, 1, 0, 1.
So
So it will be
lambda equal
1
to 1
minus
as
lambda.
Yeah.
1 minus lambda equals to 0. So lambda equals to 1. So AM is 2, right?
And only GM is 1. Only 1, 0.
GM is only because right. You can write this as this equals to this minus this, 1 minus 1. So 1 comma 1, right?
1, 0, right? The vector. So GM will be 1 and only the null space contains.
Right. Effective.
Okay.
So statement 2 is true, right?
Yeah.
1 is
Option D.
false and 2 is right. Any doubts in this, anyone?
No, sir, clear.
Right. Question number 9, you are informed A is a 2 by 2 matrix with determinant A equals to solar, right? A is 2 by 2, determinant of A is 16. We make the following statement. A is positive definite. What is determinant?
16.
Product of eigenvalues, right?
But we can't say. Maybe it is minus 4, minus 4. So
We can't say.
but
Is
A is
A
truly
invertible?
invertible. Yes.
Yes.
Non-zero
Right.
determinant.
So 1 is not necessarily true, 2 is always true. Option B, right?
Right.
Question number 10. Any doubts in question number 9?
No, sir.
Right. Question 10, let A be an A invertible real matrix and B equals to A plus A transpose, right? So B equals to A plus A transpose. Then what is correct by B minus B transpose?
Even V transpose is symmetric.
B minus B transpose will be? So
Uh,
A plus A transpose is symmetric, right?
yeah.
So B is symmetric, right? So B minus B transpose will be 0, right?
Yeah. And yeah.
And then A plus A transpose into A inverse will be A into A plus A into, right, A into A into A inverse plus A into A transpose into A inverse, right? What is this thing? This is A into A plus A transpose A inverse. What is this? Let's see. So only B minus B transpose is symmetric.
Yes.
Acha. Only this is skew symmetric. B minus B transpose is 0, right?
Yeah.
So this is 0, matlab B minus B transpose is symmetric. Is symmetric,
Right.
right? And then skew symmetric, no, not skew symmetric because you know why, right?
Right. Yeah.
And what is AB A inverse? So just take the transpose of AB A inverse. Whole transpose will be A transpose plus A inverse transpose A into A transpose, right?
Right.
Is this symmetric?
No.
No, right? Yeah, right. So is this symmetric? I don't think so. Is it? No. Any other information?
Uh,
Invertible and real? No.
maybe.
Option A is correct or what?
Yeah.
Option D. We did not check option D, right?
But one of them is non-symmetric. So the some
Some can be
must not
symmetric,
be.
right? A plus A transpose is always symmetric. So option D is true, right?
Okay, okay. Oh, right, right, right. It is the same thing.
Fine.
Oh, okay, right.
So option D is correct, right?
But okay.
Others are only saying only this is symmetric. So this is
Okay,
wrong.
okay.
Right?
Right, right.
Anything else in this problem? And doubts?
No, sir. No doubt.
So next question, let P be a real symmetric matrix and D be a diagonal real square matrix. A real square symmetric and D be diagonal, right? Each of any size, right? So P is n cross n, D is also n cross n, and D is diagonal, right? If P transpose equals to P inverse, then P is symmetric. If P is an orthogonal matrix,
Only then. So not necessary that P transposes P inverse means P is symmetric.
right? Because it's not true only for symmetric, not always, not always, right? PDP transpose is symmetric. Okay, let's
But
see.
P has been said about. Okay, okay.
PD transpose, P transpose, which is PDP transpose. This is always, right?
So this question is like, let's consider the A part once more. So
Hmm.
the given condition is P is symmetric, right?
Right. But let's not think of it like that. Let's
Okay,
think it
okay.
says it
So
implies.
independently.
Yeah,
Okay,
it implies.
okay, right.
P is symmetric. Like, I don't know what to say. Let's ignore this. Option B is
Okay,
true because this question is almost useless, right?
right. So
Right.
what about the C part? I missed that C statement which you are saying.
It
PDP
is
transpose
always
P.
symmetric. PDP transpose is always symmetric. You just check it. PDT P
Oh, right.
whole transpose, and
Yeah,
you
yeah,
see
yeah.
that it is symmetric,
Right,
right?
right. It will be. Yeah.
Okay. Last question. If A is a real symmetric matrix of size this with eigenvalue this and the corresponding eigenvectors are this, then what is this value? Anyone? It is a real symmetric matrix. Just pay attention to this thing.
And these are corresponding unit eigenvectors. So they must be orthogonal. So the inner product should be 1.
U2 dot U1 will be 0, right?
Okay. U2 dot U1 is then. Yeah. And
U3
U3
dot
dot
U1
U1
will be 0.
is 0.
Why?
So
Because
only,
eigenvectors will be orthogonal, right?
right, right. So 7 only.
Orthogonal and 7 into U1 transpose U1. What will be this value?
So 7 only. Because that is unit.
Yeah, fine. So that's all for today, right? Anyone?
Yeah.
Everyone? Do you have any doubts? Anyone? So that's it for today. So let's finish the last week's session in the next week. Last session in the next week, right? So if you have any
Yes.
doubts, you can ask me right now.
No, sir, nothing from this part. This part is clear.
Okay,
So I'll go through the
fine.
notes and ask you in the next class. And in the next class, I'll also try that part that we're trying to prove now